So basic modeling techniques and modeling concepts. In this case, let's take a look at some examples of the systems that are in this one is in the mechanical domain, this is in the electrical domain, this is a system in rotation, and this is a system or hydraulic system. So you have the effort and the flow, of course, and then we have in here a little table where you have all the efforts on the left hand side on the different systems, like the efforts can be a force on a mechanical system, or a voltage on an electrical system, or a torque on a rotational system, or a pressure on a hydraulic system. And on the right hand side here we have the flows are the velocity on a mechanical system, the current on an electrical system, the angular velocity on a mechanical system, and the volume flow rate. So what we're trying to say is that the product of any of these two is always power. And we need to emphasize that within two elements of a system, power has these two variables. They interchange the energy variables in this case. Now, if we generalize the power energy variables, we should be able to establish some relationships between them. And that leads us to this famous picture that is called Painter's tetrahedron of state, which means that if you put the effort and the flow here on this, and then on the sides you could establish that the position Q is the integral of this derivative here. Let's see if I can have right here the derivative of Q has to be F. So like you could say the position, we differentiate the position, and then the result is the velocity. Let me just get a little better in here. So the derivative of this is the flow, the derivative of this is the effort. Okay, so that is the tetrahedron of state. So we're going to be using these four variables, E, F, P, and Q. Okay, and then what are those variables across the different systems? You have for 16 variables in this case, in different energy domains: translation, rotation, electrical systems, hydraulic systems, but we define so far the effort and the flow. But we go one step further here on this table to define the displacement and the momentum. Okay, so these four variables will correspond to each one of these. So instead of using 16 as far as the notation that ultimately we use, and we use it for computer simulations, would be these four variables. Any questions about this? Okay. Now we have the idea of a word bond graph. This is an interesting concept because it illustrates how easy this technique and how close to reality it is. In this case, you have three elements of a system, three components, you could say. You have the battery, you have the motor, and you have the Bendix, which is a little gear that engages on your flywheel of the engine of in the back of the engine of your car to turn it, and of course make it, in turning it, other things happen to make it start and run. The point here is that if we have a model of the entire system, you have, like on the left hand side, the battery, the motor, and then you have the Bendix. But what is important here is what is between these two elements. Hmm? Between those two elements, we have just this bond or this junction. See? And it's joined by, between the battery and the motor, just a voltage and a current. But between the motor and the Bendix, this is going to have a torque and then an angular velocity. Okay? So what I'm trying to say is that by using simple words and the connections, we have created a bond graph. Or you could say, if you don't, if you still the word bond graph is not familiar, replace bond with connection graph maybe, junction graph. I mean, this is a bit more just, more descriptive description of this. So you have in this motor and the Bendix communicate with each other with a torque and an angular velocity. Then we have this model of a vehicle. See, the model of this vehicle indicates that we could, by using simple words and using the connection between them, we could assemble the vehicle. Like you have the engine, although the engine is composed of many parts, we consider him as a system, one, and then you have a touch and the clutch, which is a control system in itself. Then from the clutch you do the angular velocity and the torque, and then the gearbox, which is also a control component. Okay. Okay. So you have the engine interacts with the clutch with the gearbox with the drive shaft with the differential, then of course with the wheels. You realize this is like having laid out topologically your system in here, and then having made the connections between each one of the elements. Well, this might be oversimplification of the model, but it gets the point across that we are trying to do with bond graphs is a description of the system based on elements, or based on standardized components, or components of certain types is what I'm trying to say. And then these connections that occur within the elements of the system. I would say that almost this picture on the screen resembles a vehicle, huh? With with in word description. Now let's talk a little bit more technical here. If you have a component A of a system, like you have it on this case on A, and this applies a force here to B, B has to react to A. So the way we do it using this technology is we use this horizontal and vertical line. And that, what it means is that if you use like this would be a little piston that if you put your hand on the ring, you press it, you press B. So A takes an impression, an action on B, B reacts with the green signal. And on the other side, the reverse is true. In this case, B acts on A. See how the picture at the top has this effort variable. B acts on A with the effort, and A responds with the flow like this. So this is the notation for this case, this is the notation for this case. Okay. Any questions about this picture you must know in your mind? Perhaps one thing that I want to emphasize is this idea of the action-reaction and establishing the horizontal line and the vertical line together is what is called causality assignment, meaning who causes what to whom. Okay? And if you can answer that you can write down the description for the system. Now here we go. In this case, we have to begin thinking about the kind of elements that we need to model basically everything here. We established that we need at the most 9 elements. Of course, there will be some combinations between them, but 9 elements that are distinct. You have in here the two sources. You could have either a velocity source or a force source. Okay. You also have these junctions, this 0 and 1. So either the junction has a constant effort or a constant flow, depending on what it is. You lose one of those. So 9 elements, 4 of them are off the bat, very easily to understand. Okay, and then we have the rest, the other 5 on the bottom. What is it like? What is the purpose of each one of these? This is an inertia element, the element I. This is the element, the capacitor element C. Then you have the resistive element R. And in this case, you have this one that stores kinetic energy, the other one that stores potential energy, this one dissipates energy. And the two transformers. If you have a normal transformer that it is a normal transformer, let's say a set of gears transforms an angular velocity into another. Or better yet, a practical example that everybody can see. Your bike. Every bike has a sprocket with a chain, and it has a smaller gear in the back of the wheel. Okay. Let's just reflect on this a little bit. Um, what kind of transformation occurs when you pedal? Anybody? Isn't it true you pedal slow but the bike goes fast? Right? Yeah. Right. I mean, depending on which gear it is, the bike would go slower but it has more torque. And if you have in the slowest velocity, it had the highest torque. Why is that? Why is that we have this balance, let's say, more torque, lower velocity, higher velocity, lower torque? What's the reason for this? For this relationship, I would say. The answer lays in this concept of the interaction between two variables, between two elements. Effort and flows are always power. So if the power is the same, then the product of the effort times the flow, which in this case would be the torque times the angular velocity, has to be the same. And that is the case of the first two-port element called this transformer element. Yeah? And the second element is called a gyrator element. In the transformer case, it's like the sprocket. One velocity goes into another. But if the velocity transforms into a torque, or vice versa, or if the force is related to the if the force is related to the angular velocity, it's a cross relationship. It's not like relation to one member of the same family, like one velocity to another. But the case of a motor is the reason that we need this last element. See, we say that the element I, this one, will store kinetic energy, this will store potential energy, this will dissipate energy, this will transform energy, but there's only a few of these where we have a situation where the variable gets transformed like a current into a torque, or like is related, the angular velocity is related to, say, the angular velocity related to the force, the effort element, as opposed to one effort to another effort. And in the case of a motor, if the torque is related to the angular velocity, and what I'm saying, the current is related to the torque, and the voltage is related to the angular velocity. Okay. So if that's why we need this ninth element. So those are the basic elements that we need.